Module 11, Lesson 5, deals with angle relationships involving triangles. Now, this is what I think it's going to be. This is going to be a little bitty introduction to trigonometry. Mathematics has a whole course, a whole year-long course on triangles and using the angle relationships, and that course is known as trigonometry. And I've watched my youngest son do some really cool calculations with it when designing stuff for 3D printing. The pacing guide says this is going to be a 2-day lesson. Pulling it up, we're going to say that, angle relations, we have 19 slides, so 2 days is probably pretty accurate. Angles are used to design many structures, including bridges, buildings, amusement park rides. The triangles used in these structures provide strength and stability. And you can see in this bridge, there you have a lot of triangles being used, isosceles triangles coming together to give that bridge strength and stability. Let's keep going from here. Describe all the angles the triangle shown? Nah, we're not going to do that. Instead, we're going to jump straight into the learn part of our lesson, which says, a line segment definition is part of a line containing two endpoints and all of the points in between them. So we got that defined. And then we have a triangle is formed by three line segments that intersect at their endpoints. We're going to define that one. And then we'll say a point where the segments intersect, that is known as the vertex of the triangle. And then finally, the three angles that lie inside the triangle formed by the line segments and the vertices are going to be called the interior angles. So we're going to highlight all of those. Triangle XYZ, and you can see they have the X, Y, and Z right there. And it is written right here with a little triangle, just like we did the perpendicular lines with a perpendicular line, we did the parallel lines with the parallel lines. The triangle we're going to do with a triangle XYZ has sides and angles that can be named using the vertices X, Y, and Z. The angle located at vertex Y could be named angle Y, or angle XYZ, or angle ZYX. What do you notice about that? Y is going to be the middle letter in all of them. The vertex is always going to be the middle letter. You can name it by the vertex, or you can name it by all 3 points, but it's got to have that Y in the middle. The sides of the triangles can be named using segment notation. For example, line XY can be read as, side XY can be read as segment XY. Let's start pushing some buttons here and figure out what all we see. First off, you have side XY, or segment XY. You have segment YZ, also known as segment ZY, by the way, and you have segment XZ right there. We good so far? Next, you can say you have vertices X, vertice Y, and vertice Z. And then finally, we're going to look at our angles. You have angle X, which is also known as angle YXZ or angle ZXY. We have angle Y, which is also known as angle XYZ or angle ZYX. And we have angle Z, which is also known as angle XZY or angle YZX. Remember, the vertice is always going to be the middle term when you're using the middle letter when using all 3 letters to name the angle. Now our inquiry question asks, what is the relationship among the measures of the angles of a triangle? So let's get into this, and we're going to say that triangle ABC is shown. Drag one or more vertex of the triangle around to change the shape. So you can see we've got this triangle right here, and you can see the measurement of all of these angles right here. And if we drag one around, it affects all of the other angles. It doesn't matter which one we drag, the measure of the angles of the others is going to change as well. You change one point or one angle, they all change. Now, let's keep going, and we're going to push the show the sum button and see what happens when you add all of these angles up. So I'm going to hit show the sum, and you can see that currently all of those angles are equal to 180 degrees. And if I move something, it does not matter what I move, what the size of the angles are going to be, it's going to end up being, oh, wow, cool, I can go across the line too. That's pretty cool. Right there. It's going to end up being 180 degrees when you add them all up together. No matter how the angle's built, the sum of the measures of their angles is always 180 degrees. Now we're going to do something really cool. Now when we go into this, I want you to remember that the measurement of a straight line is always 180 degrees. The angle measurement of a straight line is 180 degrees, right? So watch what happens here. We're going to press the sum of the angle triangle, which is going to show us it is 180, and then we're going to show a parallel line that's going to be parallel to what the base of that triangle is. From there, we're going to create a new parallel lines, A prime and so on here. Just watch. This is actually pretty cool. No sense in reading all that to you, so we're going to zoom out just a touch. Here's our triangle, and you can see right now that we've got all three of our angles together. Of course, they all equal 180 degrees. Now we're going to add a parallel line. This line is parallel to this line right here. And next thing we're going to do is really cool. We're going to be using some of our angle rules. Remember, you have that whole transversal thing that says that this angle right here is going to be equal to that angle, and that this angle right here is now going to be equal to that angle because they're alternate interior angles. So if I take this triangle and I duplicate it and rotate it around to the right, what's going to happen? That angle is now lining up here. Same thing here. This angle is lining up here. And what are those angles equal to? 180 degrees. So you had the old top angle plus the single bar plus the double bar. All those add up to be 180 degrees, and all those are going to be the three angles that come together to make up the triangle. Don't stress this one very much. Just understand, once again, the sum of the measures of the angles of a triangle always add up to equal 180 degrees. Now let's enjoy a video from our sponsor.
Angle sum of triangles. The interior angles of any triangle have a special relationship. We can demonstrate the relationship by first tearing off each corner or angle of the triangle. Arrange the corners so they meet at one point. Notice that the angles create a straight line.
Is essentially what we did in the last problem, where we took those triangles, duplicated them, and flipped them over. All we did was match up the three corners. That's what he's doing here, once again making a straight line.
This means the sum of their measures equals 180 degrees. Let's examine another triangle. Use a protractor to measure and label the interior angles. The sum of the measures of the angles is 180 degrees. Tear off the corners and fit them together to confirm they create a straight line. This demonstration shows that the sum of the measures of the interior angles of a triangle is 180 degrees.
All right. Just more of the same. We're just hammering in the fact into your brain that sum of the measures of the angles of any triangle always is going to equal 180 degrees. Now we can take and put it right here. Once again, they said the same exact thing to you, and once again, they're showing you here's your angle, and then here's your formula, x plus y plus z equals 180 degrees. Have you figured out yet that the sum of the measured angles of any triangle is always equal to 180 degrees? If you haven't, there's not much I can do for you at this point. Find the missing angle, and what says find the value of x in the flag of St. Nick's in Nevis. I have no idea who they are, but right here, if you look really close down, let me zoom in a little bit. Actually, that didn't help a bit, did this flag stay the same way? How if I click on it? And zoom in from there and scroll. No, not going to happen. Well, this is just awful. So right here in the corner, you've got angle x. We have a right angle we know is going to be 90 degrees, and we have another angle that we know is going to be 56 degrees. So with that information, we can use the formula that they gave us, x plus y plus z is equal to 180 degrees, and write the equation x plus 56 degrees plus 90 degrees equals 180 degrees. 56 plus 90, that's 146 degrees. Subtract 146 degrees from both sides to isolate the variable. And now when you do that, you're going to find that x is equal to 34 degrees. So the measure of that angle that we were looking for is going to be 34 degrees. Oops, wrong button. 34, check it, and it checks. Easy math, nothing at all to do in these problems. Now it's going to be your turn. Go ahead and pause the video and find the missing angle x in this triangle. Now, of course, in doing that, I need to have some big kid algebraic supporting work, and I'm going to be using the old school method. Instead of saying just x, y, and z, I'm going to do it right. The measure of angle x plus the measure of angle y plus the measure of angle z equals 180 degrees. You notice that I took and put a line through my z. That's to keep it from being confused with a 2. From here, we're going to take and plug in what we know. We don't know the measure of angle x. That's what we're looking for. I'm going to call this one y and that one z. So I'm going to say plus 60 degrees plus 75 degrees. And of course, you know it doesn't matter which one you call y and which one you call z is equal to 180 degrees. Now I can say the measure of angle x is equal to, that is going to be 60 plus 75 is going to be 135 degrees equals 180 degrees. I'm going to take in, that should be a plus sign right there, by the way. I'm going to undo that plus by subtracting 135 degrees from both sides. 135. We're going to do some borrowing here. That's going to become a 7 and a 10. So when I subtract that out, I now have the measure of angle x is equal to 10 minus 5 is 5, 7 minus 3 is 4, and 1 minus 1 is 4. So our missing angle is going to be 45 degrees. Jump back over here, type in our missing 45 degrees, and the answer checks. That's all there is to doing these problems. Super simple, but you do have to show your big kid algebraic supporting work if you would like to have credit for it. I think this is a good place to end part 1 of this video. Come back and look at part 2, where we're going to start dealing with finding the measures of some more angles here with a 1 to 4 to 5 ratio. Ooh, that's going to be fun. See you in the next lesson.